Hello, and thanks for downloading the Aerospace Testing Podcast. I'm ATI's editor, Ben Sampson, and in this month's podcast, I talk to Dr. Michael Smart, Head of Research and co-founder of Hypersonix, the Australia-based developer of hypersonic vehicles and scramjet engines. Dr. Smart is one of the world's leading experts in scramjet technology, and for 10 years was a research scientist at the Hypersonic Airbreathing Propulsion branch of NASA's Langley Research Centre. He's also been Professor and Chair of Hypersonic Propulsion at the University of Queensland in Australia. This is a great chat and introduction to hypersonic technology. Dr. Smart has a great way of explaining complex things simply and real infectious enthusiasm for his area. So I'd just like to take this opportunity to tell you about our conference, which is being held in a few months' time and which Dr. Smart will be speaking at. It's called London to Sydney in 5 hours, and it's all about supersonic and hypersonic technology and testing. And yes, it is a real-life event. London to Sydney in 5 hours is being co-located with our first aerospace testing symposium in London on the 29th and 30th of September. And if you can't make it to London, the conferences will also be available online. There are more than 50 speakers at both events, which will also feature panel sessions and an exhibition from the industry's leading testing products and service suppliers. It's our launch event, so if you'd like to join hundreds of other industry professionals or just want to look at the programme and get some more information, please go to symposium.aerospace-testinginternational.com or contact anna.young@markallengroup.com. I'll say that again, it's symposium.aerospace-testinginternational.com or email anna.young@markallengroup.com. So thanks for bearing with me during the lengthy intro, and let's get on with the chat. Okay, hello Michael Smart, Dr. Michael Smart, CTO of Hypersonix, founded in 2019. Thanks for taking the time out, joining me from Australia.
No worries, Ben, good to talk to you.
Great, thanks. Could you just tell me a little bit about yourself and the company and what you're doing?
Yes, so Hypersonic Launch Systems is the name of our company. We're a startup here situated in Brisbane, Australia. We also have a business office in Sydney. And what we're doing is building scramjet engines. That's our core capability that we have, where we're leading the marketplace. And so a scramjet engine is a hypersonic air-breathing engine. So it's an air-breathing engine like a jet engine. So we use the air to generate thrust. We use the oxygen from the air rather than having to carry an oxidizer like a rocket does. So all we carry is fuel. But a scramjet is designed to work at hypersonic speed. So instead of having lots of turbo machinery like a jet engine has for compression and other things, we use shockwaves. And so our system doesn't have any moving parts. Actually, our particular scramjet engine has no moving parts whatsoever. In many ways, it's quite simple. However, it operates at hypersonic speed, and so it has all the challenges of very, very high-speed flight.
Okay. Now, a common thing for the interviewer to say here is to say, well, hypersonic, that's not that new. It's been around for a while, right? So what's different about your engine? I think it's called Spartan, right? And what are the sort of key tech?
So hypersonic technology has been around since the space age, right? So in order for a rocket to get into space, it has to go hypersonic. But when people talk about hypersonics, what they're really talking about is very, very high-speed flight in the atmosphere, where you have to deal with the fact that you've got to push the air out of the way and you've got to rub up against the air at very, very high speed, which generates heat. So you have to deal with shock waves, and then you have to deal with the heat that's generated. And what's different about our technology is, we're developing propulsion at hypersonic speeds. So we don't just have a big rocket that pushes us along at hypersonic speed and we have to deal with the friction, etc. We're actually using the air to generate propulsion, and hopefully, if we do our job right, we generate more thrust than drag, and we can accelerate. And so that's the real difference. And so when we say that our Spartan engine is a hypersonic air-breathing engine, it captures air, which we have to do very, very efficiently. Otherwise, we'll create too much drag. We then have to mix and burn fuel with that air, and we use hydrogen for a very specific reason for that. And then we add that energy, and then we have to expand the air so it goes out the back of our engine faster than it came in. And once we do that, like change the momentum of a fluid, that generates our thrust. So that's the real difference that's going on right now, is people are talking about hypersonic propulsion.
Yeah. Whereas the TEDx talk that I just watched, part of you were talking about Apollo 11, those types of that's a one-shot deal, right? It's quite a crude whoosh thing. Okay, sure. Yeah. So this ongoing propulsion that you're talking about, I mean, what are there key advances in materials, technology, or aerodynamics or design that are really underpinning what you're able to achieve at the moment?
Yeah, definitely, Ben. So there's three sorts of technologies that have come together which have really enabled us to create a working engine that could be part of a real system. The first one is computational power. Like, it's just amazing what we can simulate nowadays, and there's a significant amount of simulation that we do to design our vehicle. In the end, we do experiments, but it's really we use the simulation not to necessarily to analyze what goes on, but to design. So, to design a system that can survive, flying at Mach 10, we do a lot of simulation. So that's one of the things that's really come along. And that's true of many industries, right? Making use of simulation. The second key thing that's come along is high temperature composite materials. So these are composites that are laid up just like you're making a surfboard or some other, a wing, some other component. But through another few extra steps of processing, they can actually operate at very, very high temperatures of the order of 1,500 degrees Celsius. And if you had to look at a plate that was that hot, like, you couldn't look at it. You'd have to have your hands in the way to burn your face. Like, seriously hot materials. And they can be used again and again and again without any damage. Mm-hmm. So that is just absolutely amazing. Now, those materials, they're called ceramics matrix composites. Mm-hmm. They have been developed for like turbine blades for aircraft, or the turbine particularly, as opposed to the compressor. But the real thing has come along like in they've been around for a while in flat plate type shapes. But what's really changed in the last 5 years, I would say, is we can make our entire scramjet out of these materials. So our scramjet is not flat. It's a very curved shape. It's quite big. And we're able to manufacture real aerodynamic components out of these ceramics matrix composites. So that's a technology that's really come along. And that has broader applications, not just to hypersonic flight, but anywhere you have very, very high temperatures. Mm-hmm. And the third thing has come along, which we sort of didn't expect so much, is this real emphasis on the hydrogen economy. So hydrogen has really been looked at over the last 10 or 12 years as a automotive fuel, but also as a different energy source. And there's been a lot of technology that's been developed for automotive applications in hydrogen. Enormously high pressure gaseous tanks that can be used by buses and cars on the road. Liquid hydrogen tanks, the ability to handle hydrogen, the ability to create green hydrogen, so using solar energy to break down water and create green hydrogen. So those three sorts of quite different technologies have really come together for us. And then we've developed our own very unique scramjet engine, Spartan, which uses hydrogen fuel. But through more than 30 years of research here in Australia, we developed a scramjet that can accelerate from Mach 5 to Mach 10. And when you're traveling hypersonic, that's a massive range of operation. There's no other scramjet out there that has that sort of range of operation. And so that's what's really unique about, like, those other three technologies are available to other people, just like us, right? But the really unique thing that we've done is through a lot of research, a lot of government investment here in Australia, we've developed this world-leading scramjet engine.
Okay,
and
cool.
And just another thing about it is because our scramjets are accelerating, the real application for them is as a hypersonic platform, so a vehicle that it's used many, many times over. It's not like a one-use system. A lot of scramjet work that's done all over the world at the moment they're one-use systems, if you know what I mean. But our system, we're able to really make an expensive system because it's going to be used many, many times over. And so our aircraft, our Delta Veloz aircraft, which is powered by the Spartan scramjet, once it's done its mission, it can come back and land just a normal plane. And so that's really key to our business model and everything that we do.
That was my next question, actually, Michael. The Delta Veloz orbiter. I mean, that obviously is going to be quite further down the line. You need the engine first, right? I mean, how are you sort of you still at the design stage with that, or?
Well, no. So what we're doing. So the engine has been developed over many years, but as well as doing our research on engines, we've learned a lot about hypersonic vehicles as well. And so what we are doing in the company is we're building an MVP, so a minimum viable product, which is our Delta Veloz, which is it's a reusable hypersonic aircraft. It has, ailerons, moving tails, all the sorts of things that it would be on any small aircraft. It's fully autonomous, and it's about 6 meters long. So it's actually sort of the minimum size that we could do, a useful commercial productive mission with. And the whole focus of the company right now is to build a prototype of Delta Veloz. We're deep in the design phase right now, and then take that and go and fly it, and not just fly it once, but fly it twice, because the whole point of our system is it flies back and it's reusable. So our goal is to fly it twice, and that's the plan that we're on. And over the next, our plan says 28 months from now, we will do that flight. So that's sort of the timing of everything that we're doing. Yeah, I know. Yeah.
28 months is pretty quick. Yeah, time. I mean, just for the benefit of the listeners, could you describe the design of Delta Veloz? I mean, is there an inspiration behind it? I mean, what's the key elements of the design?
Yeah, so it's a hypersonic aircraft. So think of Concorde on steroids. So that's what it'll look like. It doesn't have as big a wings as Concorde, because when you're traveling hypersonic, you're generating so much pressure on the surfaces of your vehicle. You don't need a lot of wing. I don't know, the listeners might know the X-15. So that was the rocket plane from the 60s. That was a hypersonic aircraft as well. And it came back and landed and did 199 missions. I think there were 3 vehicles. So that's sort of our inspiration as well. So that's what we're trying to do. So hypersonic aircraft.
So before we talk about the where you are in the testing and development of Spartan, could you just describe to me the applications that you have in mind? Are you talking about, how far, you're going all the way into space? You're talking about taking passengers and cargo up beyond the atmosphere? I mean, what's the kind of use case?
Yeah, so the use case that is easiest is as part of a reusable small sat launch system. So all the little small sat systems that fly right now, they're all one use, right? So point and shoot, one use, and they have these enormously long supply chains to build, because they're throwing them away. So our system is designed to be a part of a fully reusable small satellite launch system that, because it's reusable, will be more economic than throwing things away, but it's also will be quite able to be quite responsive. So it'll sort of be sitting in the garage waiting to go. And there's a lot of interest now on responsive access to space. So historically, you plan 2 years ahead for a space launch and everything. They build everything, they put it together, and then they launch it. But if you've got a system that's just sitting there waiting to go, and say one of a key satellite that's used for imagery or part of a commercial communication system goes down, like we can put up 2 weeks later. So that's really the main short-term application for our technology is reusable space launch. Now, in the longer run, the scramjet engines are reusable and could be thought of as a propulsion system for airlines, but they do have the limitation that they don't work until you get to Mark 5. So there's another propulsion system required, and there's lots of work going on in different places about how to develop essentially a jet engine that can operate from 0 to Mark 5. Once that technology is in place, then the scramjet can enable you to go to Mark 7, Mark 8, and can be part of an airline system. But the thing about developing aircraft for people is people, like to watch movies. They like to survive. They like oxygen. So it's, there's a lot of tech that needs to be added to the propulsion system in order to make something that you or I will want to fly on.
Yeah.
Safely.
Way down the line, yeah, I guess. So let's talk about where you're at with the testing, what you're actually doing. You mentioned the computer simulation and a lot of the design work, of course, and then you reach a stage, I guess, where you have to start validating stuff, start actually doing some physical experimentation. Where you're at the moment, and what's the next kind of big milestone you're looking at?
Yeah, so where we are now is so we have our Spartan scramjet design, and at the start of this year, during February and March, we did a series of 111 experiments in a hypersonic wind tunnel at the University of Queensland. And this facility, it's called a free piston shock tunnel. It's able to recreate the exact conditions of flight of the scramjet engine, all the way from Mark 5 to Mark 10, not in the same experiment. So we would do an experiment Mark 5 and then one at Mark 6, all the way to Mark 10, different fueling configurations. And it was really what it was a flight qualification test for us. So we knew the sort of thrust levels that are required for our system, and we basically went into the wind tunnel to check that we're able to do that. And actually, the engine worked better than we had hoped. So we're extremely pleased about that. So the current phase is we're now manufacturing a working scramjet engine. So we use out of these ceramics matrix composites, where that's being built, not in Australia, unfortunately. That capability isn't in Australia. So we're having it manufactured in Europe. We are building the hydrogen fuel system that we would need. At this present time, our MVP has a hydrogen fuel tank, which is where we store gaseous hydrogen at 700 atmospheres, so 70 megapascals, which is an absolutely enormous pressure. And through lots of work technology development's been done in the automotive industry, we're able to fill that tank in 5 minutes. This refueling system it's almost like magic to someone like myself, an engineer like myself. But it's designed to, you pull over on the Autobahn with your car and you plug it into the hydrogen system and it fills your tank to 700 atmospheres in 5 minutes. It's absolutely amazing tech. So at the moment we're building our fuel system. And so early next year, we're going to put the scramjet and the fuel system together. We can't operate the scramjet at hypersonic speed in the lab, but we've already done that. What we're doing is we're going to take the fuel system and the scramjet through what's called hardware in the loop testing. So we'll run a mock trajectory essentially many times over and look at different problems that we might have and understand how the system responds. So that's really our near-term goal. And as I say, in terms of engineering, but in terms of design, we're deeply in the stage of designing our Delta Veloz vehicle right now. And there's a lot of thermal analysis that we need because it gets really hot.
Yeah. Okay. So that when you start the hardware and the loop testing next year, I mean, would that be a fully integrated system? That'll be everything put together, or yeah.
Yeah, that's the idea. Yeah, because the part of the funding that we're using for that, it's for the Department of Industry here in Australia, and it's commercialization funding. So essentially, we're developing that engine system as an engine that could be used by other companies, for example, to power a hypersonic aircraft. So it's really been developed as a system in itself. But we, of course, want to, in order to prove that system works, we need to go and fly it ourselves. And so that's what the Delta Veloz is about.
Okay. Is there anything else particularly innovative about what you're doing? Perhaps the approach? I mean,
I think on the space side of things, so I would say that we aim to be a new space company. So our core competency that we have that's ahead of the pack is to build scramjet engines. And so our plan is not to reinvent all the other parts of Delta Veloz that we would need to fly it. So we're going to partner with other high-tech companies, maybe small companies like ourselves, to put that whole system together. So we're not going to reinvent any wheels. We're going to go to the best in class and form partnerships to build this Delta Veloz system. So I think that's actually quite different to lots of the space companies. They're all very vertically integrated, these space companies. They want to make every nut and bolt themselves, and every tank and every actuator, which of course they then go and throw away, because it's this very long supply chain. And if you have a problem with that supply chain, well, you're stuffed. But for us, we're developing an aircraft. So it's a completely different business model for the space industry. And I think, once we prove this technology, that you can fly to space, I think it's going to change a lot of the thought processes that go on in the space industry. So we would see ourselves as a disruptor to the space industry, a completely different business model. And so apart from the technology, that's a really important thing, I think, that we're trying to do.
That fundamental change in the business model, perhaps one day with Hypersonic, but that kind of idea of reusable vehicles reaching space, the cost coming down. And do you think that's a change we're going to see within our lifetimes?
Definitely, yeah. The thing about our scramjet technology is that particularly here in Australia, we've been working on it for 30 years, and so it's very mature in itself. And so there's no new equation we have to solve. There's no new technology that we have to add. Everything is in place. So we're planning to be launching small sats with our system 5 years from now. That's the plan. But that flight of our MVP 28 months from now, that's obviously a key technology hurdle that we need to get past to really prove that we have a working, functioning system.
Okay. Sure. All right. And how about a hypersonic aircraft? I've got to ask because the conference has titled it. How about a hypersonic aircraft, London to Sydney? What is it, 5 hours or 4 hours?
Oh, no, it's London to Sydney is like 3 hours.
Okay.
I think it's less than 3 hours.
Possible?
Probably more time getting out of London to Heathrow than it takes a flight. But maybe not quite that. It is. But as I said earlier, the technology needs to prove itself with these other applications first. And then I think, I really believe technology doesn't, in engineering, not so much in physics where you're coming up with new ideas, but in engineering, technologies take steps, but they don't take massive steps because you're not sure where to take that step to. But if you take relatively small steps, you learn a lot, then you go, oh, I know where my next step needs to be. And I think that's what will happen. with this hypersonic technology. We can get a system that works for small sats, system that's very maneuverable, not point and shoot like a standard rocket system. People will come up with new ways of using that. And then, if the other propulsion systems come along and speed up a bit, then they'll put the high-speed jet engine and the scramjet together. And then we'll be looking at how to fly Sydney to London in 3 hours. So, I think it'll be, as we move this technology along, it'll be much clearer about which way is the best way to go.
Great. Okay. I think that's a great place to finish, Michael. Thank you for your time very much. I agree with you. I think there's always small steps.
So, thanks for listening. I hope you enjoyed it and maybe learnt a thing or two. I certainly did. Remember, you can catch Dr. Smart at the London to Sydney and Aerospace Testing Symposium in September in London, either in person or online. Go to symposium.aerospace-testing-international.com for more details and a look at the programme and, of course, the opportunity to register. See you next episode and have a great day.